The very last section of this chapter is entitled Complex Numbers. So up to this point, you and I have been working in the real number system. But now we will expand to a larger number system called the complex number system. To get us started, let us begin with a definition for the imaginary unit. So the imaginary number I is defined as the square root of -1. Now, in the real number system, the square root of -1 is not real. It's not a real number. There is no real number such that when you square it, you get -1. But in the complex number system, there is a solution to this expression, and we call it I. Now notice that what follows from this statement is that I squared is equal to -1. All we would have to do is square both sides. When you square I, you get I squared, and when you square the square root of -1, you're left with -1. These two equivalences should be known really well by you. So what this does for us is so many things. It allows us to write the square root of a negative value in terms of I. Like, watch this. In this first example, check this out. Write in terms of I, the imaginary number. So the square root of -49. Now, if we were living in the real number system only, we would say, oh, no solution, or no real number solution. But now that we have I defined, we can rewrite this in terms of I. So here we go. Using the product rule for radicals, we can rewrite this as the square root of 49 times -1, right? And furthermore, it is equal to the square root of 49 times the square root of -1. This is the product rule for radicals. We all know that the square root of 49 is 7, and now the square root of -1, that's exactly what I is equal to. So then the square root of -49, the square root of -49 is 7i. What I like to tell students is that whenever you see a negative underneath the square root, that generates the imaginary number I. And then so once you've accounted for the fact that the negative generates I, you can kind of ignore it. I'm going to see if I can cover it up right there. And then the square root of 49 is just 7. So the square root of 49 is 7, and then the negative gives you I. The next one is the square root of -19. Now, again, I'll use the product rule for radicals. I won't show my work like this all the time, but just because we're getting started, I'm going to kind of take it step by step here. So I've used the product rule to rewrite this as the square root of 19 times the square root of -1. Now, the square root of 19 does not simplify like the square root of 49 does. Because 19 is not a perfect square, neither does it have a factor that's a perfect square. So the square root of 19 just stays. But the square root of -1 is I. The best place to put the I is in front. So it's I times the square root of 19. That's the simplification for this. That's rewriting this in terms of I. Okay? The next one says the negative square root of -12. I'm going to read this differently, though. I'm going to interpret this as the opposite of the square root of -12. One thing is for sure. Do not make these two negatives become a positive. You're not multiplying these two negatives, okay? So I rewrote it as the opposite of square root of +12 and the square root of -1. This is me using the product rule. So I'm going to continue simplifying. We know that the square root of 12 is the square root of 4 times the square root of 3. And then that square root of -1 on the back end is I. I'm going to continue simplifying. We know that the square root of 4 is 2. I'm going to write the I next to that and then end it with the radical, square root of 3. Okay? Notice where I put the I. The I is best in front of the radical and not on the back end. Okay? We have the square root of negative 18 over 121. All right, let's do it together. First of all, I am going to give the numerator its own square root, the denominator its own square root. That's the quotient rule for radicals. And then I'm going to go ahead and jump the gun here a little bit. The negative underneath the square root is going to generate I. So I already know that, so I'm going to go ahead and put an I on the back end. Now, the square root of 121 is a perfect square, so that's just 11. And the square root of 18 can be rewritten as the square root of 9 times the square root of 2. Don't forget I. So then your final answer can be rewritten as 3 root 2 over 11, and then I'm going to have I hang out next to the fraction. Now notice where I put I here, okay? When I have a fraction like this, I always put I next to the fraction bar on the right. You don't have to do it that way. You can rewrite it this way if you'd like. 3I root 2 over 11. That's fine as well. But when I have a fraction, I usually put it beside the fraction bar. Don't put it next to the square root of 2, like up here, part of the numerator on the back end of the radical. That would be a bad idea. All right, here's our definition for a complex number. A complex number is any number that can be written in the form a plus bi, where a and b are real numbers and I is equal to the square root of negative 1. Now, complex numbers of this form, a plus bi, where b is not equal to 0, so when b is not 0, these complex numbers are also called imaginary numbers, okay? Now, I want to have a conversation about calling a complex number imaginary, okay, and calling an imaginary number a complex number. But first, let me show you a diagram of where we are right now in this number system. So, I want you to check this out. The natural numbers is probably one of the smaller sets of numbers here, which is kind of weird to say because it's also an infinite set of numbers. But the natural numbers are your positive whole numbers starting at 1. So natural numbers are 1, 2, 3, 4, 5, 6, 7, 8, and so forth. It starts at 1. The whole numbers are your positive whole numbers starting at 0. So the only difference between the whole numbers and the natural numbers is that the whole numbers include 0. The natural numbers do not include 0. So the whole numbers are 0, 1, 2, 3, 4, 5, and so forth. Your integers are your negative and your positive whole numbers. So like negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5, and so forth. All right? Your rational numbers are numbers that can be written as a fraction where the numerator and the denominator are integers, right? So like 1/2 is in there, negative 1/3 is a rational number, 7/10 and negative 100/5 or whatever, any fraction is written as a rational number. Now, if a number cannot be written as a fraction with integers as the numerator and the denominator, then you're talking about an irrational number. And an irrational number is a decimal that never stops and never repeats in a pattern. Some popular irrational numbers are like pi. The number pi is an irrational number. The number e, which you and I will study later on in this course, is an irrational number. The square root of any number that's not a perfect square is an irrational number, like the square root of 5, the square root of 20, the square root of 8, the square root of 10, the square root of 7, and so forth are irrational numbers. Now, we've been living in the real number system. The real number system are all of your rational numbers and all of your irrational numbers. So in this blue family, this is where we've been up to this point. And now we introduce complex numbers of the form a plus bi. Now, complex numbers of the form a plus bi are also called imaginary numbers. So a plus bi where b is not 0. So for example, the numbers like 2 plus 3i is an imaginary number. 5 plus 4i is an imaginary number. 8 plus 2i is an imaginary number, right? If b is 0, it'll wipe, if A is 0, if A is 0, then it'll be 0 plus 5i, or 0 plus 7i, or 0 minus 2i. If this first term is 0, you call it a pure imaginary number. When A is 0, all you have left, if A is 0, then it goes away, and all you have is bi, the bi part, the imaginary part, and so it's called a pure imaginary number. Now, if you take all of your real numbers and all of your imaginary numbers together, all the real numbers and the imaginary numbers, you have this larger number system called the complex number system. All right, I'm going to give you some numbers, and I want you to tell me what kind of numbers they are. So here you have 4 plus 2i. Is this a natural number? No. Whole? No. Integer? No. Rational? No. Irrational? No. It's actually not a real number at all. It's not a real number because of the imaginary number here. Notice that in order for you to be a real number, this coefficient of I has to be 0, right? That's what, in order for you to be a real number. And it's not 0, it's actually 2. So this is an imaginary number, also called a complex number. So this is both a complex number, you can also call it an imaginary number. I want to give you a little bit more terminology here. This first term is called the real part of the imaginary number, and 2 is called the imaginary part because it's attached to the imaginary number. All right, so every complex number has a real part and an imaginary part, a real part and an imaginary part, okay? So the real part is 4, the imaginary part is 2. What kind of number is this? 7 minus I. This would also be considered an imaginary number. You can also call it a complex number. Now, the real part is 7. The imaginary part, be careful, is -1. -1 is the imaginary part. Now, what kind of number is this? This is imaginary. Yes, it's an imaginary number. It's also considered a complex number, and you can also call it a pure imaginary number because, watch this everybody, you can rewrite 5i as 0 plus 5i. So 5i is just the complex number whose real part is 0. That's why you didn't see it. The real part is 0 and the imaginary part is 5. That's what pure imaginary numbers are. The real part, which is a, is 0, right? The real part is a, which is 0. And whenever the real part is 0, it's called a pure imaginary number. So you can technically call 5i a complex number, an imaginary number, a pure imaginary number, right? Its most broad name, its most general name is a complex number. You can be more specific by saying it's an imaginary number, and then you can be most specific by saying it's a pure imaginary number because the real part is 0. Now this one might be tricky. What kind of number is this? Well, to help us, let us consider 8 as 8 plus 0i. Yes, 8 can be rewritten like this. So 8 is really, watch this, now this might kind of blow your mind a little bit, but 8 is actually a complex number. It's a complex number whose imaginary part is 0. Whose imaginary part is 0. So, can you call this, number 8, can you call it pure imaginary? No, you can't call it pure imaginary because in order for it to be pure imaginary, the real part would have to be 0, and the real part is not. The real part is 8. So it's not pure imaginary. Is it an imaginary number? No, it cannot be an imaginary number because in order for you to be an imaginary number, your imaginary part, which is b, cannot be 0. And that's exactly what my imaginary part is. So 8 is not a pure imaginary number. It's not an imaginary number. Can I call it a complex number? Yes, it is a complex number. The real part is 8, and the imaginary part is 0. Now, can you also call it a real number? Well, of course, 8 is a real number. You can locate it on the number line, the real number line, your x-axis. Notice that your real numbers are just complex numbers whose imaginary part is 0, which is exactly what I have here. But wait a minute, is 8 also rational? It's not written as a fraction, but can you write it as a fraction? Of course you can. 8 can be rewritten as 8 over 1, or 16 over 2, or 24 divided by 3. There's infinitely many ways to write 8 as a fraction, so it's rational. Is it irrational? No. A number cannot be rational and irrational. It has to be one or the other. So it's rational, it's an integer, it's whole, it's natural. So 8 has a lot of names. So look at all these names that the number 8 has. It's complex, it's real, rational, integer, whole, natural, right? It's basically this, and this, right? So what is this? 6 different names for the number 8. Okay, so all of the numbers that you and I have been discussing, all these real numbers, have been complex numbers all along. Complex numbers whose imaginary part is just 0. That's mind-blowing. Now, you're used to having lots of different names, right? I mean, so this doesn't surprise you too much because, like, for example, I am a father, I am a husband, I am a brother, I am a son, I'm an amazing teacher, right? And that's kind of a joke, but we all have a lot of names. You have a lot of names probably, right? So the same way, this number 8 has a lot of names. All right, example number, actually this is example number 2, not example number 1. Sorry about that. I'll change that real quick. We already did example 1. All right, so example number 2, I want us to write each of the following numbers in the form a plus bi. Now keep in mind, when you write a number in this form, it's called standard form for a complex number. So this is standard form for a complex number. All right, here we go, guys. The first number they want you to rewrite in standard form is 23. So all they really want you to do is rewrite this so that you can see the real part and the imaginary part. So basically, they want you to rewrite 23 as 23 plus 0i. That's it. All right, that's all they wanted you to do. So 23 is equivalent to 23 plus 0i. The square root of negative 144. All right, so then this is going to be equal to, now watch this, the square root of 144, positive 144, is just 12. And then the negative underneath the square root gives you I. Now, this can't be your final answer because they want standard form. They want to see the real part and the imaginary. So 12i is the same thing as 0 plus 12i. So this is standard form for this complex number. 5 plus the square root of negative 18. All right, so then this is 5 plus. The square root of 18 can be rewritten as the square root of 9 times the square root of 2, and then you're going to have an I, right, because of the negative underneath the square root. So then it's 5 plus, watch this, 3, that's the square root of 9, I root 2. Again, please notice where I'm choosing to write the imaginary number I. Okay, don't put it on the back end of the radical. All right, very good, everybody. That's rewriting a complex number in standard form. All right, everybody, the rest of this lesson, and we're already almost done, the rest of this lesson is just going over how to operate on your complex numbers. So we're going to go over adding and subtracting of complex numbers, multiplying complex numbers, and dividing complex numbers, and then we're done. So let's add or subtract some complex numbers. All right, so here we have 4 minus 14i, okay, that complex number, plus 12 plus 56i. Now, both of these complex numbers are written in standard form, so I'm going to go ahead and operate on them now. Notice that 4 is the real part, negative 14 is the imaginary part. 12 is the real part, 56 is the imaginary part. So how do you think we're supposed to add these two complex numbers? It's kind of like combining like terms. So what we want to do is add the real parts together. So 4 plus 12, those are the real parts. And then add the imaginary parts together. Negative 14 plus 56. Now these are the imaginary parts, so let's put the imaginary number on them, right? So you're adding your real parts, 4 and 12, and negative 14 and 56, your imaginary parts, right? So it's very much like terms. So then you get 16 plus 42i. So this is the sum of these two complex numbers. Next we have 22 minus 11i minus 5 plus 2i. Now be careful here. The real part is 22. The imaginary part is negative 11. The real part is 5. And the imaginary part is positive 2. What you might want to do, and this is optional, okay? You don't have to do this, but what you might want to do is distribute this negative here and add the opposite. Just because it's sort of easy to make a sign error here, so be careful. And I've seen a lot of students make a sign error, so you may want to rewrite this as 22 minus 11i, right? Nothing changed there. But now this is addition of negative 5 and minus 2i. That's one way to do this. Now, when you add, now you're adding, okay? So you're going to add the real parts together, right? Add the real parts together. Those are the real parts. And add the imaginary parts together. Don't forget the imaginary unit there. So you get 22 plus negative 5, which is the same thing as 22 minus 5, which is 17. And then you get negative 11 plus negative 2, which is negative 13. So you get plus negative 13, and then don't forget I. You can make this look simpler by just doing 17 minus 13i. So I invite you to rewrite subtraction as the addition of the opposite. It might help you not, or might help you avoid there. It might help you avoid a sign error. All right, this next one is not written correctly. So I will not operate. I will not add until each of these complex numbers are written in standard form. Now that's very important. Before you operate, make sure the numbers are written in standard form. Remember, standard form is a plus bi. So here we go. So then this number is 9 minus 7i plus 2 minus 8i. Okay? Again, be very careful. These two negatives don't make a positive. Same thing here. They don't make a positive, so be careful. Now that we can see these numbers in standard form, we could do 9 plus 2, those are the real parts, plus negative 7 minus 8, those are the imaginary parts, right? This is the same thing as negative 7 plus negative 8. All right, so then this is 11, and then you're going to have plus negative 15i, right? Which can be rewritten as just 11 minus 15i. And that answer is definitely in standard form. Now, we're done with adding and subtracting. That was pretty straightforward, I hope you feel. So now all we have to talk about is multiplication and division. Check out this example. It's very important. Before I multiply, let's write these in standard form first, all right? So then this is the square root of 5, I, right, times I times the square root of 45, like that, okay? Now these are written in terms of I at least, right? Now we can use the product rule, okay? You could not use the product rule before and get the right answer, okay? So here, I get I times I, which is I squared, and then we have the square root of 5 times 45. Now, I'm going to write this as 5 times 5 times 9, okay? This 5 right here is that 5. And then 45 I wrote as 5 times 9. So, don't forget that in the very beginning of our lesson, we said I squared is equal to what? Negative 1. So we have negative 1 on the outside times, now do you see that This is the square root of 25. The square root of 5 times 5 is the square root of 25, which is just 5. And then do you also see that the square root of 9 is 3? So then our final answer is negative 15. I think it was better to do this problem this way than to multiply 5 and 45 together and get this huge number, and then we have to simplify. All right. Now, I want to show you something, everybody. If you would have done this problem differently, if you would have used the product rule in the very beginning, notice how you get the wrong answer. Now watch this. The square root of, if you say, well, the product rule says this, that the product of these square roots is equivalent to the square root of their product, then notice that a negative times a negative is a positive. So now your radicand is positive, and you have 5 times 5 times 9, right? And the square root of 25 is 5, and the square root of 9 is 3, and you get positive 15. Obviously, positive 15 is different than negative 15, and this is the wrong answer. And it's wrong answer because before you operate, you must rewrite these in terms of I first, right? Write them in terms of I first. All right, let's continue with the multiplication. Now here, everybody, there is really nothing, to be honest with you, there's really nothing brand new here. Let's distribute the negative 3. Now, we're used to doing that already, right? So then what we get then is negative 12 plus 15i. And that's it. Okay, that's it. I mean, it is what it is. I'm sure you're like, put that on the exam or put that on a quiz. I'd get that 100% correct. And I know you will, because this is pretty simple, right? Let's do another. All right, now we have 6i times 2 minus 5i. Again, nothing new here except for the fact that, so I'm going to distribute as I'm talking, except for the fact that, remember, I squared is equal to negative 1. I squared, don't forget that I squared is equal to negative 1. If you remember that, then you're going to be fine, okay? Now, 6i times 2 is 12i. 6i times negative 5i is negative 30i squared. Now, don't forget that I squared is equivalent to negative 1. So then this turns out to be 12i plus 30. Usually we write the real part first. Let me rewrite this as 30 plus 12i. That wasn't too bad, was it? I mean, it was distribution like you've always done. The only thing that you have to be cautious about is don't forget I squared is equal to negative 1. Okay, we're still talking about multiplication. 3 minus 5i times negative 2 plus 6i. Now, I hope that your gut is telling you, or your instinct is telling you, to distribute. Some of you call it FOIL, and that would be correct. So let's distribute. All right, so then what we get is 3 times negative 2 is negative 6. 3 times 6i is 18i. Negative 5i times negative 2 is positive 10i. And then negative 5i times 6i is negative 30i squared. All right, so then this is negative 6, and then notice that these two here are like terms that you can combine. So then that gives you plus 28i, and then minus 30 times negative 1 because of that I squared. So then this becomes negative 6 plus 28i plus 30. You can add the real parts, negative 6 and 30 together, to get positive 24, and then plus 28i. How did that problem feel for you? I hope that went smooth for you. Here we have a product of two numbers, but the problem is that neither one of them are written in standard form. So before we operate, make sure they're in standard form. That's very important. So here, this can be rewritten as 4 plus 5i, and then this one can be rewritten as 1 minus 2i, okay? And now we can distribute. 4 times 1, 4 times negative 2i, 5i times 1, 5i times negative 2i. So then what we'll get is 4 minus 8i plus 5i minus 10i squared. Combine the two middle terms, negative 8i and 5i, which will give you negative 3i. And don't forget that I squared is negative 1. So then you have 4 minus 3i plus 10. You can combine the 4 and the 10 to give you 14. And so your final answer is 14 minus 3i. All right, now we're going to move to division. But before we talk about division of complex numbers, there's a very, very, very important concept we need to talk about. Find the product of, so we need to multiply, negative 2 plus 7i and its complex conjugate. All right, I just took away that apostrophe on the word its, okay? Anyway, negative 2 plus 7i and its complex conjugate. Now, remember that a complex conjugate is just the opposite operation, okay? It's not the opposite number. It's just the opposite operation. So, negative 2 plus 7i, its complex conjugate, is going to be negative 2 minus 7i. So they want us to multiply this number that they gave us by its complex conjugate. Okay, this is the complex conjugate of this number. Notice that the only thing that I changed was the operation from addition to subtraction. All right, so let's distribute. And the reason why we're doing this is because I really, really, really want you to notice, take special note of what our answer is going to be. Negative 2 times negative 2 is positive 4. Negative 2 times negative 7i is positive 14i. And then positive 7i times negative 2 is negative 14i. 7i times negative 7i is negative 49i squared. Now pay close attention. Notice that your imaginary terms cancel. Okay, that was so important what just happened right there. And then you end up with 4 minus 49, watch this, times negative 1, because I squared is negative 1. So you end up with just 4 plus 49. You end up with just the number 53. Now, the amazing thing is this answer is not an imaginary number. This answer is just a real number. This will always happen. The product of any complex number and its complex conjugate will always be just a real number. These imaginary parts will always cancel. To prove what I just said, I just took any complex number, a plus bi, and I'm multiplying it by its complex conjugate. Now, these just represent any complex number, okay? So this is going to be true for all complex numbers, right? So when I distribute a times a and then a times negative bi, bi times a and then bi times negative bi, I get a squared, then I get negative abi, then I get positive abi, and then I get negative b squared I squared. Notice what just happens, but what happens here, those imaginary parts cancel, like I said, always happens. So you get a squared minus b squared. Now don't forget, I squared is negative 1. So this just becomes a squared plus b squared. Now remember that in our definition for complex numbers, both a and b are real numbers. All right, in our definition, both a and b are real numbers. So when you take a real number and square it, and another real number and square it, and add them together, you'll get a real number as a sum. So a squared plus b squared is definitely just a real number. Now this leads us to our last objective, which is division of complex numbers. Here we go. All right, everybody. Here we have 5 divided by 3 plus 2i. Now listen carefully. The strategy here is very similar to what we were doing in section 4 of this chapter, 9.4. We were rationalizing radical expressions. I hope you remember that the way we rationalized in 9.4 was we multiplied the numerator and the denominator by the conjugate of the denominator. It's the same strategy here. Let's multiply the numerator and the denominator by the complex conjugate of the denominator. All right, the complex conjugate of 3 plus 2i is 3 minus 2i. Now we must multiply the numerator and the denominator by the same expression so that you're really multiplying by 1. And whenever you multiply an expression by 1, you're not changing its value. All right, so let's go for this, everybody. Let's do this. In the numerator, all you have to do is 5 times 3, and then 5 times negative 2i. In the denominator, I'm going to do more than I need to for this first example. 3 times 3, which will be 9, 3 times negative 2i, and then I'll do 2i times 3, and then 2i times negative 2i. I'm doing more than I need to because I showed you how the imaginary parts will always cancel whenever you multiply a complex number by its complex conjugate. In other words, watch this. 3 times negative 2i is negative 6i, while 2i times 3 is positive 6i. So negative 6i and positive 6i will cancel. We expected that, right? We proved it. And so this product and this product need not be shown, right? I really can skip these two products here because they're always going to cancel. But I'll go ahead and show it in this example here. All right, so here we go. So then you're going to get 5 times 3 in the numerator, which is 15. You're going to get 5 times negative 2i, which is negative 10i. That's the numerator. Now the denominator, 3 times 3 is 9. Now 3 times negative 2i is negative 6i. 2i times 3 is positive 6i. And then 2i times negative 2i is negative 4i squared. Now this is the part I feel like is a waste of time. We expected those to cancel. So I feel like I could have saved myself a little bit of work here. So now we have 15 minus 10i. Now the denominator is 9 minus 4 times negative 1. Don't forget that I squared is negative 1. All right, so let's continue simplifying this. Hey, don't forget that the instructions say write the answer in the form a plus bi. So in other words, write it in standard form. Remember that standard form means I can see what the real part is and what the imaginary part is. All right, remember that when we get to the end. All right, let's continue simplifying. So then we have here 15 minus 10i over 9 plus 4. So then we have 15 minus 10i over 13. Now this is not your final answer because, like, what would be your real part? It might be a little confusing as to what your real part is and what your imaginary part is. So standard form says separate your real part from your imaginary part. So then this is 15 over 13 minus 10i over 13. So we're going to rewrite it like this. The first term over the denominator minus the second term over the denominator. This must be the way you write your final answer for complex numbers, always in standard form. So your real part is 15 thirteenths. Your imaginary part is negative 10 thirteenths. Okay, 3 minus 2i divided by 2 minus I. Let's multiply the numerator and the denominator by the same thing, and that is the complex conjugate of the denominator, 2 plus I. All right, let's go. Now, we're going to have to distribute, all right? So the numerator, 3 times 2 is 6. 3 times positive I, I'm not sure you can see that. Let me move this up a little bit. 3 times I is 3i. let's continue. Let's see, negative 2i times 2 is negative 4i. And then negative 2i times I is negative 2i squared. All right, let's go to the denominator. I'm only going to show this product and this product, okay? Because I already know that the other products will cancel. That is to say, 2 times I is 2i, and negative I times 2 is negative 2i. Positive 2i, negative 2i will cancel, so I'm not even going to bother. So I'm only going to do this first product and this last product there. All right, so anyway, 2 times 2 is 4, and then negative I times positive I is negative I squared. All right, so then in the numerator, you end up with 6 minus 1i. I got minus 1i by combining these two like terms. And then minus 2 times negative 1. The denominator, 4 minus negative 1, because I squared is negative 1. Now you have 6 minus I plus 2 over 4 plus 1. So you have 8 minus I over 5. The final answer, written in standard form for a complex number, is 8/5 minus 1/5 I. Okay? Now, another way you can write this in standard form, if you like, if you prefer, you can write it as 8 over 5 minus I over 5, okay? But I like to see what the imaginary part is. The imaginary part is negative 1/5. The real part is 8/5. So I prefer this way here. All right, let's go to example 9. We're going to divide and, of course, write our final answer in a+bi form or standard form. But before we divide, everybody, let's write these in the right form, right? Let's write these in standard form. The numerator should be rewritten as 2 plus 5i. And the denominator should be rewritten as 6 plus 15i. Don't forget that 15 squared is 225. Oh, you know what I just realized? Look at the denominator. Can't the denominator be factored? Let's see. The numerator is 2 plus 5i. But what is this denominator? If you factor out, let's see, a 3. I think 3 is a GCF. You end up with what? 2 plus, 5i. Oh, look at that, everybody. 2 plus 5i divides out with 2 plus 5i. And so all you're left with is, man, this problem turned out to be really nice. You're left with 1 in the numerator and just 3 in the denominator. So your answer is 1/3. 1/3 is the answer. But in standard form, right, for a complex number, 1/3 plus 0i. Man, I didn't have to multiply by the conjugate at all because this just simplified really nicely. All right, last example. Let's divide, and don't forget to write your answer in standard form, okay, for a complex number. 11 divided by 6i. This is the first time where what you're dividing by is a pure imaginary number. This is pure imaginary. I want you to realize something, that the denominator can be rewritten as 0 plus 6i, can't it? Now that's important to see because now we multiply by the conjugate of the denominator. The conjugate of the denominator is just 0 minus 6i, right, everybody? Now, for me, I feel like there are too many zeros here. So I'm going to do this work. I'm going to do all of this work right here, but I'm going to drop all of these zeros. I don't need them. So in other words, 11 over 6i can just be multiplied by, if you just drop the zeros, negative 6i. Negative 6i. All right? So that's simpler without having to write all of these zeros here. You can do this whenever the denominator is just pure imaginary. Okay, so let's do the work. So the numerator is just negative 66i, and the denominator is negative 36i squared. Okay, which then gives us negative 66i over positive 36. This I squared is negative 1, negative 36, times negative 1 is positive 36. We can simplify here. The the GCF between 36 and 66 is 6. So I'll divide the, let me write this for us. I'm dividing by the GCF. I'm going to divide by 6. I'm going to divide by 6 in the numerator and denominator, of course. And negative 66 divided by 6 is negative 11i. And then 36 divided by 6 is 6. Let's not forget to write our final answer in standard form for a complex number. So 0 minus 11 over 6i. This is our final answer written in standard form for a complex number. Now, that wasn't too bad. However, I want to show you something else, okay? This is the problem that they gave us, 11 over 6i. We could simplify this process a lot by just multiplying by I itself, okay? By I itself. And you can do this because I divided by I is just 1, so you're really multiplying by 1. And you can do this, just multiply by I, just I, whenever the denominator is pure imaginary. So watch this. Notice what the answer is. I'm going to scroll back down. This is the answer. I'm going to show you how you can get the answer by just multiplying by I, okay? So the numerator is just 11i, and the denominator is just 6i squared. What is I squared equal to? Negative 1. So then here is my negative, and then you have 11 over 6i, right? 11 over 6 I. And then you have a negative from the I squared, okay? Written in standard form is 0 minus 11/6 I, which is exactly what we wrote down earlier. This was way less work because I just multiplied by I. So, rule of thumb, if you are dividing complex numbers and your divisor, the denominator, is pure imaginary, you can just multiply by I in the numerator and denominator, and that'll do it.